Look up on a clear night, and the stars seem fixed, serene, eternal. But everything you see is in motion, the moon around the earth around the sun around the galaxy, every body falling endlessly under the pull of gravity. Celestial mechanics is the science that predicts those motions, and it is the oldest quantitative science we have. Its story unfolds in three great acts. In the first, Johannes Kepler distilled the shape of planetary motion into three simple laws. In the second, Isaac Newton explained those laws with a single universal force. And in the third, Henri Poincaré discovered that the moment you add a third body to the dance, prediction itself begins to break down, that hidden inside the clockwork of the heavens lies mathematical chaos. This is the story of how we learn to predict the sky, and of where that power reaches its limit. The first act belongs to Kepler, and to the man whose data he inherited. In the late 16th century, the Danish astronomer Tycho Brahe compiled the most precise naked-eye observations ever made, positions accurate to about 1 or 2 arcminutes, a small fraction of the width of the full moon. When Tycho died, those priceless records passed to his assistant, Johannes Kepler, who spent years wrestling with the orbit of Mars, trying to force it into the circles that astronomy had demanded for 2,000 years. The circles would not fit, the data were simply too good to ignore, and Kepler, almost in despair, was driven to a radical conclusion. The orbit was not a circle at all, but an ellipse. From that struggle came 3 laws that remade astronomy. The first, every planet moves in an ellipse with the sun at one focus, not at the center but offset, at one of the 2 special points that define the oval. The second, the line joining a planet to the sun sweeps out equal areas in equal times, which means a planet must move fastest when it is closest to the sun and slowest when it is far away. And, the third, the harmonic law, the square of a planet's orbital period is proportional to the cube of its average distance from the sun, so the further out a planet lies, the disproportionately longer its year. Kepler published the first 2 laws in 1609, and the third a decade later, in 1619. They were exact, they were beautiful, and they were utterly mysterious. Kepler had found the laws of planetary motion, but he had no idea why they held. The explanation waited for Isaac Newton, and it arrived in 1687, in what may be the greatest scientific book ever written, the Principia. Newton proposed a single law of universal gravitation. Every pair of masses in the universe attracts every other, along the line joining them, with a force that grows with the product of their masses and falls off as the square of the distance between them, double the separation, and the pull drops to a quarter. From that one inverse square law, using the calculus he had invented for the purpose, Newton derived all 3 of Kepler's laws as mathematical theorems. The equilateral law, he showed, follows from any force directed toward a center, but the ellipse and the harmonic law require specifically the inverse square. In a single stroke he unified the heavens and the earth. The same force that pulls an apple to the ground holds the moon in its orbit and turned astronomy from description into prediction. The strength of that force is set by the gravitational constant, about 6.67 times 10 to the minus 11 in metric units. Still, to this day, the least precisely measured of all the fundamental constants of nature. To see how prediction actually works, start with the simplest case: 2 bodies alone in space, attracting each other and nothing else. This is the 2-body problem, and it is one of the rare gems of physics that can be solved exactly. At first it looks daunting, 2 bodies, each with a position and a velocity in 3 dimensions, but it simplifies dramatically, because the only forces are between the 2 bodies. Their common center of mass drifts at a constant velocity and can be set aside. What remains is the motion of one body relative to the other. The whole system collapses to a single fictitious particle orbiting a fixed center of gravity, the so-called Kepler problem. Solve that, and you have solved the motion of the moon about the Earth, of the Earth about the Sun, and of a spacecraft about a planet. What makes the Kepler problem solvable is a set of quantities that never change as the body moves. The first is angular momentum, a measure of the body's motion around the center. Because gravity always points straight toward that center, angular momentum is conserved, and this single fact confines the orbit to a fixed, flat plane and gives Kepler's equilateral law directly. The second conserved quantity is energy, the sum of the body's motion and its position in the gravitational well fixed for all time. And there is a third, subtler one unique to the inverse square law, a vector that points steadily from the focus toward the closest point of the orbit and never wavers. Its constancy is the reason a Keplerian ellipse holds its orientation in space and does not slowly rotate. This hidden extra symmetry of the inverse square force is the deep mathematical reason the two-body problem can be solved at all, a piece of good fortune that almost no other gravitational problem shares. From the conservation of energy comes the single most useful equation in all of orbital mechanics, the vis-viva equation, from the Latin for living force. It states that the square of a body's speed equals the gravitational parameter times the quantity 2 over its current distance, minus 1 over the semi-major axis, that is, 1 over half the long dimension of its orbit. In plainer terms, if you know the size of an orbit and where the body currently sits upon it, you know exactly how fast it is moving, and it carries a profound corollary. The total energy of an orbit depends only on its semi-major axis, on its size, and on nothing else at all. A tight orbit is a fast, low-energy one, a wide orbit is a slow, high-energy one. Negative energy means a bound orbit that always returns, exactly zero energy means a body that just barely escapes to infinity, and positive energy means an unbound path that never comes back. A concrete example shows why this centuries-old mathematics still runs every space mission. Consider a spacecraft in a circular orbit a few hundred kilometers up, in low Earth orbit, the realm of the International Space Station. Feed the size of that orbit into the vis-viva equation, and out comes its speed, about 7.7 kilometers per second, some 25 times the speed of sound. Kepler's third law then gives the time to circle the Earth once, about 92 minutes, which is why astronauts aboard the station see a fresh sunrise roughly every hour and a half. And to break free of the Earth entirely from that altitude requires the escape speed, which the same equation shows is always the square root of 2, about 1.4 times the local circular speed, here just under 11 kilometers per second. 3 centuries after Newton, the motion of every satellite still falls out of 2 conserved numbers and 1 conserved vector. The full family of two-body orbits is the family of curves the ancient Greeks called the conic sections, the shapes you get by slicing through a cone. A single number, the eccentricity, selects which one you have. An eccentricity of 0 is a perfect circle. Between 0 and 1 is an ellipse, a closed and bound orbit that carries the body between a nearest point and a farthest point. The planets ride gentle ellipses, Earth so nearly circular you could scarcely tell, while a comet like Halley's sweeps along a long, thin ellipse far out and back. An eccentricity of exactly 1 is a parabola, the knife edge of escape. And anything greater than 1 is a hyperbola, an open path that swings past once and departs forever. When the interstellar visitors Oumuamua and Borisov passed through the solar system, they came in on hyperbolas, never bound to the sun at all. And every time a spacecraft swings past a planet for a boost, it rides a hyperbola in that planet's frame. Newton's version of Kepler's third law contained a hidden gift that Kepler himself could never have seen. In its exact form, the square of the period depends on the cube of the orbit's size divided by the total mass of both bodies, not merely the mass of the central one. Because the sun so overwhelmingly outweighs its planets, Kepler's simpler statement holds to great accuracy across the solar system. But that dependence on mass quietly turns the law into a cosmic weighing scale. Point it at a pair of stars orbiting each other, measure their period and their separation, and it hands you their masses. Point it at the tiny wobble a hidden planet induces in its star and it reveals that planet's mass. Point it at a moon circling a world and it weighs the world itself. Kepler's harmonic law, made exact by Newton, became the chief instrument by which astronomers weigh the universe. There remains a practical difficulty. Knowing the shape of an orbit is not the same as knowing where the body will be at a given moment, because a planet races through its closest approach and dawdles. At its farthest, its position does not advance evenly with the clock. Relating time to position requires what is now called Kepler's equation, and it has a frustrating property. It is transcendental, meaning it cannot be untangled with any simple formula. Instead, one must solve it by successive approximation, refining a guess over and over until it settles. This is no historical curiosity. That little iterative loop, solving Kepler's equation, runs billions of times a day, inside every satellite navigation receiver in every phone, inside planetarium programs, and inside the flight computers of spacecraft. A 300-year-old equation is quietly at work every single time your phone finds where you are. To pin down an orbit completely in 3-dimensional space takes exactly 6 numbers, called the orbital elements, matching the 6 pieces of information carried in a body's position and velocity at one instant. 2 of them fix the orbit's shape and size, the semi-major axis and the eccentricity. 3 more orient that orbit in space, the tilt of its plane, the direction in which the plane is turned, and the angle around to the closest point within it. And the 6th locates the body along its track at a chosen instant. In the ideal 2-body world, 5 of these 6 numbers are permanently fixed, and only the last, the body's position, along the orbit changes with time. Feed 6 orbital elements into a computer, and you have specified an orbit entirely. Where it lies, how large it is, how it is tilted, and where the body rides upon it. Real orbits, of course, are never perfectly Keplerian. A dozen small effects, the gravity of other bodies, the drag of the thin upper atmosphere, the faint pressure of sunlight, and above all the fact that no planet is a perfect sphere, make the orbital elements drift slowly over time. The Earth bulges at its equator, and that bulge tugs on satellites in a way that makes their orbital planes gradually rotate. Mission designers do not merely tolerate this drift, they exploit it. By choosing an orbit's tilt just so, they can make the Earth's bulge swing the orbital plane around at exactly 1 turn per year, keeping the satellite always at the same angle to the Sun. Nearly every Earth observation and reconnaissance satellite flies such a sun-synchronous orbit. Choose instead a different critical tilt, about 63 degrees, and the orbit's low point freezes in place, letting a communications satellite linger for hours over the far north. What looks at first like a nuisance becomes a precision tool. One tiny orbital drift, however, refused for decades to be explained, and in the end it cracked open Newton's universe. The planet Mercury, closest to the Sun, has an orbit whose point of nearest approach slowly rotates around the Sun. Astronomers could account for almost all of that rotation as the combined pull of the other planets. But a stubborn remainder, just 43 arcseconds per century, a mere hair's breadth of an angle, would not yield to any Newtonian calculation. The discrepancy was flagged as early as 1859, and it haunted celestial mechanics for over half a century. The resolution came in 1915, when Albert Einstein's general theory of relativity recast gravity not as a force, but as the curvature of spacetime and predicted, with no free parameters to adjust, exactly 43 arcseconds per century. Mercury's wandering orbit became one of the first and most decisive proofs that Newton's law, magnificent as it is only an approximation to a deeper truth. For all its triumphs, the 2-body problem is a fragile paradise, and it shatters the moment a third body joins the dance. The 3-body problem, 3 masses pulling on one another from arbitrary starting points, has no general solution in terms of ordinary functions, and worse, it is what mathematicians call non-integrable. There simply are not enough conserved quantities to tame it. This was established in the most dramatic fashion. In 1889, the King of Sweden offered a prize for the solution of the problem, and the great French mathematician Henri Poincaré won it. But as his memoir was being printed, an editor's question exposed a subtle error, and in repairing it, Poincaré stumbled onto something astonishing. The motion, he found, could be infinitely intricate. Trajectories starting from almost identical conditions would diverge apart exponentially, becoming utterly unpredictable. He had discovered deterministic chaos 3/4 of a century before it was rediscovered in the mathematics of weather forecasting. Chaos in the heavens does not mean the planets are about to scatter. Their orbits are broadly stable and will remain so for billions of years. What it means is subtler and stranger. The solar system's exact configuration cannot be predicted forever. Detailed computer integrations find that the inner planets have a so-called Lyapunov time of only about 5 million years, beyond which their precise positions along their orbits become fundamentally unknowable, the tiniest uncertainty today amplified into total ignorance then. The clockwork is real, but it is a clock that cannot be read too far ahead, and yet within the chaos, islands of perfect order survive. Euler found configurations in which 3 bodies stay strung along a straight rotating line. Lagrange found one in which they sit at the corners of a rotating equilateral triangle. There is even, discovered only in recent decades, a delicate orbit in which 3 equal masses chase one another forever around a single figure-8, proof that the 3-body problem, centuries on, still holds surprises. The most useful tractable version of the problem strips it right down. 2 massive bodies, say the Sun and the Earth, circle their common center, while a third negligible body, a spacecraft, drifts in their combined pull without disturbing them at all. In the frame of reference that turns along with the two large bodies, something remarkable appears: 5 special points where all the forces balance, and a small body can sit at rest relative to the two giants. These are the Lagrange points, labelled L1 through L5. 3 of them lie in a line through the two bodies and are unstable. A spacecraft there will slowly drift away, like a ball balanced on a saddle, unless it is gently nudged back. The other 2 sit at the apexes of equilateral triangles, and, provided the 2 main bodies are unequal enough in mass, they are genuinely stable gravitational hollows where drifting material naturally collects. Both kinds of Lagrange point are now dotted with real objects. At the stable triangular points of the Sun and Jupiter, more than 1 million Trojan asteroids have gathered over the long age of the solar system, shepherded and held there by gravity, and the unstable points strung along the line, for all their delicacy, have become prime real estate for spacecraft. The point between us and the Sun hosts solar observatories that keep an unbroken watch on our star. And 1.5 million kilometers out on the opposite side in the Earth's shadow sits the point now occupied by the James Webb Space Telescope, which slid into its orbit there in January 2022, a location permanently shielded from the Sun, the Earth and the Moon, ideal for a telescope that must be kept bitterly cold. Because the point is unstable, Webb must fire its thrusters every few weeks to keep its perch, a tiny, unending correction to stay balanced on the saddle. Celestial mechanics becomes astrodynamics, the engineering of spaceflight, the moment you add a controllable rocket to the picture. Because a rocket burns for only seconds or minutes, briefly compared with an orbit that lasts hours, engineers treat each firing as an instantaneous change in velocity, measured by a quantity they call delta V. Delta V is the true currency of space travel, because the rocket equation ties it exponentially to the propellant you must carry. Modest increases in delta V demand punishing increases in fuel, so the whole art of trajectory design is to reach your destination for the least possible delta V. The classic answer for moving between 2 circular orbits is the Hohmann transfer, an elegant ellipse just tangent to both, requiring only 2 engine burns, one to leave the inner orbit and one to settle onto the outer. Follow a real example: lifting a satellite from low orbit up to the geostationary belt, some 36,000 kilometers high, where it circles once a day and so hangs fixed above one spot on the turning Earth. The first burn down low flings the craft onto a stretched transfer ellipse. A coasting half-orbit later, a second burn at the high point rounds the path off into the final circle. Add the 2 together, and the total comes to about 3.9 kilometers per second of delta V, with a coast of roughly 5 hours in between. And every one of those numbers is computed straight from the vis-viva equation, the very same relation between speed and position we met at the beginning. The abstract jewel of the two-body problem is, quite literally, the tool that sizes the fuel tank. Journeys between the planets need one further idea, and it is a beautifully pragmatic cheat called the patch conic method. The true problem, a spacecraft pulled at once by the Sun, the Earth, the destination planet, and everything else is hopelessly tangled, so mission designers cut it into pieces. Near the Earth they pretend that only the Earth's gravity matters, and the path is a simple 2-body curve. Once far enough away, they hand the spacecraft over to the Sun's gravity alone, and it coasts on a 2-body orbit around the Sun. Near the destination, the target planet takes over in its turn. Each leg is an exactly solvable 2-body arc, and the legs are patched together at the boundaries, where one body's grip gives way to the next. An intractable many-body problem is thus reassembled out of pieces we can solve perfectly, and it is accurate enough to plan an entire mission before a single number is refined by brute force computation. The most spectacular payoff of this thinking is the gravity assist, the slingshot. When a spacecraft swings close past a moving planet, it leaves with the same speed relative to that planet as it arrived with. But in the frame of the Sun, the encounter has swung its velocity around and added a slice of the planet's own enormous orbital motion. So the craft gains speed and energy, essentially for free, borrowing an imperceptible amount from the planet's vast momentum. This is how the Voyager probes toured the outer planets, riding a rare alignment in the late 1970s from Jupiter to Saturn and on outward. It is how the Cassini orbiter reached Saturn, by way of Venus, Earth and Jupiter, and it is how the Parker Solar Probe uses repeated swings past Venus to shed energy and fall ever closer to the Sun. The humble 2-body flyby, chained together again and again, has carried our machines clear across the entire solar system, all of this prediction is only as good as the tables of positions it rests upon, and those tables have a name, ephemerides. For centuries they were computed by hand from long mathematical series. Today the finest of them are made by numerically integrating the motion of the entire solar system, the Sun, all the planets, the Moon, and hundreds of asteroids, forward and backward in time, with the corrections of general relativity built in, and then fitting the whole vast calculation to a mountain of observations, laser beams bounced off reflectors left on the Moon, radar echoes from the planets, radio tracking of distant spacecraft. The gold standard, produced by NASA Jet Propulsion Laboratory, is a series whose latest editions appeared in 2021, accurate enough to land probes on comets and to test Einstein's gravity across the solar system. The distance from the Earth to the Sun, once the supreme unknown of all astronomy, is now simply a defined constant, fixed by international agreement down to the meter. There is one last ingredient without which all this precision is meaningless: knowing exactly when. Predicting where a body will be is empty unless you can say when it will be there, and time itself turns out to be surprisingly slippery. Because the Earth's rotation is subtly irregular, and because Einstein's relativity makes clocks tick at different rates depending on their motion and their depth in gravity, celestial mechanics needs several distinct timescales at once. There is atomic time, kept by the steady beat of atomic clocks and utterly uniform. There is a terrestrial time used for Earth-centered predictions, offset from atomic time by a fixed 32 and a fraction seconds. And there is a barycentric time, referred to the center of the whole solar system, on which the great ephemerides are actually computed. Ordinary civil time, the time on your wall, is the least suited of all to astronomy, kept in step with the wandering Earth by the occasional insertion of a leap second, a patch so troublesome that the world's timekeepers have now agreed to abolish it by the year 2035, and so celestial mechanics lives along a sharp and beautiful boundary. On one side lies the two-body problem, a dual, exactly solvable, its conserved energy and angular momentum yielding perfect conic section orbits, and the vis-viva equation that still sizes every rocket. On the other side lies the three-body problem and everything beyond it, where Poincaré's chaos makes perfect, eternal prediction impossible in principle, and the science must proceed instead by special solutions, clever approximations, and raw computation. The genius of the field is to live productively across that divide, taming interplanetary flight with patched two-body arcs, parking flagship telescopes at Lagrange points, and grinding out relativistic ephemerides accurate to the meter. And genuine mysteries endure. The long-term fate of the solar system is not proven, and the calculations hint at a small but real chance that Mercury's orbit could run wild before the Sun dies. 3.5 centuries after Newton's Principia, celestial mechanics remains at once the most successful of all our predictive sciences, and a living frontier, where the oldest questions about the motion of the heavens are still not fully answered.